So you can see, right now we're up here under second law of thermodynamics. And we already stated that the first law of thermodynamics said, hey, you can't create nor can you destroy energy, but you can alter it in form. Now, the second law is even kind of cooler. Here's that same steam that was coming to my turbine a minute ago. And I'll put a tandem flow turbine here like we had. And we know that that steam went across blades in both directions, and then it exited the turbine. Well, if I was to send, I'll just use a weird unit, I'll say 100 units of energy to this turbine. What the second law says is no engine, no heat engine, no matter if it's real or ideal or perfect, no, even imaginable, could result in this. I can't convert all of the energy that I send to a process or through a plant. I can't convert all of the energy to actual usable rotation. That would be C, 100, 0, and all of it would now become work of this turbine. This is impossible. That's what the second law says. It says no engine, real or ideal, when operating in a cycle, can convert all of its heat that's supplied to it to useful work. Not possible. There is going to be a huge energy amount coming out of a high-pressure turbine. High-pressure turbine is not a hugely efficient device. When we start looking at the change between inlet to outlet, we don't get near as much as we do out of a low-pressure turbine. So this is going to be an important concept. Additionally, the question is often asked, why? And it brings up this concept of entropy. Now, it was one of those knowledge requirements, entropy and enthalpy. And this one is entropy. We are right here. It says a consequence of the second law is the development of a new property here called entropy. And it essentially is introduced to explain the feasibility of a process being able to happen. The feasibility we saw of a perfect turbine is not going to happen. That turbine has got to have a change in enthalpy across it, and it cannot convert all of the useful energy that I sent to it to work. So the reason it can be explained is the last paragraph here on the left. Entropy is explained as a measure of the unavailable heat to perform work. So every bit of energy cannot be converted to useful work because there is a portion of it that is unavailable to do that. And that is defined as entropy. Entropy is S. That's the symbol for entropy. And it is BTUs per degrees Rankine. It's on an absolute scale. But once again, I don't care about the whole amount of entropy in a process or a cycle. What I care about is specific entropy. So it changes the unit a little bit. I know I'm only going to look at the entropy change of 1 pound mass. So that becomes BTU per pound mass degrees Rankine. So that's the unit for entropy. And here's the deal. When it comes to entropy, the unit for entropy on our Mollier diagram that we'll get to in, let me get that camera to refocus. On a Mollier diagram, when we look at it, a Mollier diagram is what's known as an HS diagram. So it's going to have enthalpy on one side, here on the vertical axis, and here on the horizontal axis, it's going to have entropy. And the units, like we said, are for this entropy, and it's a specific entropy, is BTUs per pound mass degrees Rankine. Well, on this Mollier diagram that we're going to look at, we'll see the unit starts at 1 and ends all the way up here at 2. We don't really care what the value of the entropy is. We just want to know if this was the value initially when I started, is it constant or is it increasing after the process is over? I will tell you, just to kind of jump ahead a little bit, Any real process, a turbine, a reactor, a condenser, a pump, must increase its entropy. An ideal turbine can have a constant entropy. So what it's useful to do is when I can determine what the ideal turbine, how much enthalpy it would change. There's the change in enthalpy across that turbine. I could figure that out, and we know that that was work, remember? Work of that turbine was equal to its change in enthalpy, and here's a change in enthalpy across a turbine, but it assumes no increase in entropy. Entropy was constant. The real turbine, though, didn't extract as much energy out because it had an increase in entropy. Entropy should just be thought of as another property created to help us describe the thermodynamic processes. It's an important concept to remember. And you must realize any real process must increase entropy. This here, with no change, is an ideal process. So it's always nice to figure out the ideal work of the turbine, and then my real turbine and our engineers, we can start working towards that, doing whatever we have to do to increase the efficiency, extract as much energy out of the working fluid to make this turbine work better. However, I'm never going to get there because all real processes must increase entropy. So the work of the real turbine will always be less than the work of the ideal turbine. Continuing on, entropy accounts for some pretty cool things. We know that specific entropy was entropy divided by mass, so that was BTUs per pound mass degrees Rankine. What I really care about, though, is change in entropy. And I know that the closer I can get to zero change in entropy, the closer I'm getting to that straight line drop across an ideal turbine. So entropy is a difficult thing. It's there to help us describe the unavailable work that's available, that's not available rather in our working fluid. It kind of describes whether or not a process is feasible. When I take an egg, for instance, and I crack it, and so I got the shell. Here's the shell, and I've got a yolk, and it's a bad egg. So I've got a green yolk here, and I've got the white here. Well, so far I haven't done anything, but I haven't taken anything away. I still have the entire egg here, all four parts, 2 shell pieces, and a white and a yolk. And now I'm going to put it in a frying pan, and I'm going to heat it up. There's my flame. And now I'm going to make scrambled eggs, and I'm going to put scrambled eggs in here. So all I did was take the pieces and add heat and a little bit of motion. Okay, we stopped there. Okay, why don't I see if I can get back to my original starting point of an egg? It's ridiculous to think about, but what would I have to do? Well, can I take the eggs that are here, remove them, and cool them down and put them in my ice box, the refrigerator, 33 degrees, cool them way down. Here's my scrambled eggs. Are they going to turn back to an egg yolk and egg white? If they did, then I could take the egg yolk and egg white, put it back in here, and then I could duct tape up the eggshell, and I got back where I started. But we all know that's not possible. This is not a reversible process. And the way we account for this is entropy has increased during this process. It's a real process. So entropy increased when we heated these eggs.